Turn our attention to problem 13.5. Here we have a formula of C8H14O2. Okay, we notice that we have a peak at 170.5 ppm. We'll go through and do our IHD analysis and find that we have an IHD is equal to 2. We can also check the number of protons that are on carbon atoms. We see that all 14 of our protons are on carbon atoms. We also see two elements of symmetry in this molecule, indicated by peaks, which are doubled at 31.7 as a triplet and 23.8 as a triplet. Okay, so looking at our functional groups pointing to 170.5, again, that's coming as a singlet. And we know that 170 is too far upfield to be related to a ketone or an aldehyde. Also, it's a singlet, so it cannot be an aldehyde. So that leads us to point out that this compound must be an ester or a lactone. A lactone is a cyclic version of an ester. And we don't have any other alkene or unsaturated functionality, so that also leads us to think that we have a ring in this molecule. Okay, we pointed out that we have an element of symmetry with our peaks at 31.7 and our peak at 23.8. Okay, so we'll indicate that with this hashed line separating those two methylenes, indicating that we've got an element of symmetry. We do have a ring. Rings are an easy way to build in symmetry, so we're going to think about that as a possibility here for these methylenes. Okay. All right, so then continuing on, we're going to look at our tables now, so we can go to our table. We can see that it's completely consistent that we have our peak at 170.5 is coming from an ester functionality. Okay, so we will consider that. We also note that we have a singlet at 2.03 in the proton NMR. Going and then looking at our peaks, remembering for esters where things come, we know that if we have again, the line refers to a methyl group, open circles to a methylene, and closed circles to a methine carbon. If we have the methyl group directly attached to the carbon of the ester, we would expect that to come at about 2.0 ppm. So we're going to assign that peak here at 2.03 to a methyl group which is attached to the ester functionality. Now, if we have a group that is attached to the oxygen of the ester, we expect chemical shifts of about 3.6, 4.1, and 4.9 respectively. We see this peak here at 4.75, which is a multiplet worth 1 hydrogen. So it's worth assigning that as the peak that is associated with the oxygen of the ester as a methine. Okay, so then with that, there's really only one way left to put this together. We know that we have a ring, we have no other methyl groups, and we just have two sets of methylenes that are symmetrical and an additional methylene to plug in. And then we have 10 hydrogens that will go associated with this ring. So here's the answer.